The amount of voltage applied to an electrical circuit and the overall resistance of the circuit define the electric current flowing through it. The flow of electric current through the circuit will be boosted if the circuit resistance is reduced. Increased circuit resistance, on the other hand, decreases the passage of electric current through the circuit. One can control, increase or reduce, the flow of electric current in the circuit by inserting the rheostat into the electrical circuit. The electric current flow is reduced by a rheostat to a specific level. It does not, however, entirely stop the passage of electric current. Infinite resistance is required to totally impede the flow of electric current. It is impossible to entirely stop the electric current in practice. I intend to show the application of electric current regulation in electric circuit with rheostat by designing an animation in PowerPoint. So stay with us until the end of this movie. First, I plan to design the restaurant. I use a ready-made shape like a rectangle for this design. Construction of rheostat. The coil is a high-resistivity alloy and is adjustable from the runner. The output pin consists of 3 pins, of which 2 poles are fixed at the top of the resistor and the other pin is the moving pole. In the 19th century, Sir Charles Wheatstone invented the rheostat using a long tube with coiled wires around it and an adjustable slider. The word rheostat is made of 2 words, rheo meaning flow of current in Greek and stat meaning stationary instrument. When placed in an electric circuit, the flow of electricity changed through 2 terminals, one terminal near the sliding contact and the other connected near the bottom. Rheostat applications. Rheostat is generally used in applications where high voltage or current is required, such as changing the light intensity of a light bulb. An increase in the resistance of the rheostat decreases the flow of electric current, leading to dimming of lights and vice versa. Generators. Motor speed. Heater and oven temperature control. Volume control. Rheostat has 3 terminals, which I am designing. How does a rheostat work? If we want to alter the amount of current flowing across a circuit, we have 2 options. We can change either the resistance on the circuit or the voltage being applied to it. This relationship is represented by the basic Ohm's law equation, commonly written as V equals IR, where V equals voltage, I equals current, and R equals resistance. Strictly speaking, V equals IR is the formula for the definition of electrical resistance, although for most practical purposes this is functionally interchangeable with Ohm's law proper. It should be noted that a rheostat does not change voltage directly, the applied voltage remains constant across both component and circuit, unlike in a potentiometer. Instead, a rheostat adjusts current, and thus in effect voltage, by increasing or decreasing resistance. Precisely how it does this will depend on the type of rheostat resistor being used. Different rheostats have varying maximum power and resistance ratings, stated in watts and ohms respectively. A linear rheostat, for example, changes resistance by dragging a sliding wiper that is in contact with a straight wire coil. Meanwhile, controlling resistance using a rotary rheostat involves turning a knob or dial to sweep the wiper around a U-shaped wire coil. Other basic rheostat types use similar but slightly different methods. To answer the question how do rheostats work, it is important to understand how to wire a rheostat circuit. We need to highlight the role of the terminals and connections on the resistor. A potentiometer uses 3 terminals, 1 at each fixed end, and a third connection at the sliding contact or wiper. A rheostat uses just 2 active terminals, one of which is fixed to either fixed end, the other can be left alone or grounded, while the second is connected to the wiper. As such, a potentiometer can be made to function as a rheostat by disconnecting one of the fixed terminals. A rheostat, however, cannot be made into a potentiometer by reversing the process. As the rheostat is connected via one fixed terminal and one sliding contact, the active length between these two connections can be altered when the wiper is moved along a wire coil. The path taken by the electricity bridging these connections is therefore either elongated or shortened. In simple terms, this mechanical length adjustment is what creates variable resistance on the circuit, enabling the rheostat to alter and control current flow from A to B. The ohm is the common unit of electrical resistance, equivalent to 1 volt per ampere and represented by the capital Greek letter omega, omega. The resistance of a wire is directly proportional to its length and inversely proportional to its cross-sectional area. Resistance also depends on the material of the conductor. The electrical resistance of an object is a measure of its opposition to the flow of electric current. Its reciprocal quantity is electrical conductance, measuring the ease with which an electric current passes. Electrical resistance shares some conceptual parallels with mechanical friction. The SI unit of electrical resistance is the ohm, omega, while electrical conductance is measured in Siemens, S, formerly called the mho and then represented by. The resistance of an object depends in large part on the material it is made of. Objects made of electrical insulators like rubber tend to have very high resistance and low conductance, while objects made of electrical conductors like metals tend to have very low resistance and high conductance. This relationship is quantified by resistivity or conductivity. The nature of a material is not the only factor in resistance and conductance, however, it also depends on the size and shape of an object because these properties are extensive rather than intensive. For example, a wire's resistance is higher if it is long and thin, and lower if it is short and thick. All objects resist electrical current, except for superconductors, which have a resistance of 0. Resistance wire is an alloy wire which produces some level of resistance to an electric current. It is commonly used to create heat in a heating element, although, before the advent of solid-state controls, it was used to regulate the current in electrical circuits. Heating elements are found in space heaters, toasters, cookers, and hair dryers. Electrical resistance heaters are also used in many industrial environments including electric smelting furnaces and food processing machinery, as well as in the automotive sector for preheating components in internal combustion engines to reduce emissions when they start up. Now I am going to design a lamp. The reason for the design of the lamp is that when I change the resistance of the electric circuit with the help of a rheostat, by changing the intensity of the lamp, we will realize that the intensity of the current is changing because the value of the resistance is changing. You can design the lamp in any shape you like or download ready-made shapes from the internet. Of course, to make animations, it is better to design the shapes yourself, because in this case you can give desired effects and animations to your shapes. Okay, well, this design is very easy. For professional design, it is better that you design with graphic software, but for faster and easier design, use PowerPoint. For now, I complete my animation with these simple but scientific forms. Because I need an electric circuit for my animation, so besides the lamp, I have to have other devices, such as an ammeter that can measure the change in electric current. So I have to design it with PowerPoint. Perhaps the most difficult part of the ammeter is its grading part. With the ready-made form in PowerPoint, this problem can be solved to some extent. But for its professional design, we need help from Illustrator. If you are creative, you can design a good shape with PowerPoint. Ammeter, instrument for measuring either direct, DC, or alternating, AC, electric current, in amperes. An ammeter can measure a wide range of current values because at high values only a small portion of the current is directed through the meter mechanism. A shunt in parallel with the meter carries the major portion. An ammeter, abbreviation of ampere meter, is an instrument used to measure the current in a circuit. Electric currents are measured in amperes, hence the name. For direct measurement, the ammeter is connected in series with the circuit in which the current is to be measured. An ammeter usually has low resistance so that it does not cause a significant voltage drop in the circuit being measured. Instruments used to measure smaller currents, in the milliampere or microampere range, are designated as milliammeters or microammeters. Early ammeters were laboratory instruments that relied on the Earth's magnetic field for operation. By the late 19th century, improved instruments were designed which could be mounted in any position and allowed accurate measurements in electric power systems. It is generally represented by letter A in a circuit. Now we have to design the energy generator in the electric circuit, i.e. the battery. To save time, I previously used the simple form and the tools available in PowerPoint, such as freeform, and designed this battery. Now I have to paint it. Batteries provide the energy to push the charges through the resistors in the circuit by converting chemical potential energy into the electrical potential energy of the charges. Electricity travels in circuits. Electricity must have a complete path, or electrical circuit, before the electrons can move. The switch or on-off button on all electrical devices closes, turns on, or opens, turns off, an electrical circuit in the device. Turning or switching off a light opens a circuit and electrons cannot flow through the light. Turning on a light closes a circuit, which allows electricity to flow from one electric wire, through the light bulb, and then through another wire to complete a circuit. Edit point tool is always useful in designing with PowerPoint, so don't neglect it. Okay, the battery is almost ready and I need to copy it to the first slide and resize it a bit to fit the size of my slide. The last part of the electrical circuit is the switch, which is very easy to design. Just be careful, some of its parts are electrically non-conductive and I separate them with different colors. OK, with the freeform tool, we easily connect the connecting wires between devices, rheostat, ammeter, lamp, and on/off switch. Now add your own animation according to your taste but with scientific methods and edit your animation with the Edit Point tool. For example, here I coordinate the path of electrons with the path of the connecting wire. You can animate many electrons, but I have animated only one of them in this animation. The more coiled coils in the rheostat, the more resistance you can create in the electrical circuit. Note that the electrons pass through the roller and move towards the B terminal, since the length of the wire has a direct effect on increasing the resistance. As the roller moves towards the B terminal, it adds to the resistance, and as a result, the current decreases and the intensity of the light increases. The lamp will decrease and you should pay special attention to it in your animation. Thank you for watching this educational video.